noise cancellation application with National Instruments CompactDAQ. It features simultaneous analog input and output with two different modules, and we'll discuss those in just a moment. Also, it uses LabVIEW graphical programming to program the application, and we'll show you how to do that in just a second after we describe our hardware setup. In CompactDAQ we have two modules. This is the 9233, and this is a 4-channel IEPE dynamic signal input module that's capable of 50,000 samples per second per channel and 24 bits of resolution. This is an analog output module. It's the 9263, and this is a 4-channel 100 kilosample per second simultaneous update device that has 16 bits of resolution. We're going to use the 9263 to generate two simultaneous analog waveforms that come out to these amplified speakers. These will be sine waves, and we'll play them and they'll be directed toward one another. What we will do then is change the phase independently of those two sine waves, and when they're in phase they'll have a maximum amplitude. When we get them 180 degrees out of phase, they'll have a minimum amplitude. We're going to measure the amplitude of those combined sine waves with this microphone right here. This microphone comes back around and will be read by the 9233 analog input module. This then will be read in LabVIEW, and we'll be able to see the change in the amplitude as the cancellation effect happens when they go out of phase. So let's go into LabVIEW now and begin to program our application. The first thing we're going to want to do is put a meter on the front panel so that we can read the RMS value of the combined sine waves that come into our microphone. So we're going to scale this from 0 to 0.05. Next, what we would like to do is put two sliders on our front panel that's going to allow us to independently change the phase of each one of those sine waves that we're generating. So we're going to scale these between 0 and 180 degrees, and we'll create a copy of this, and we'll have our two sliders. So that's our front panel, pretty straightforward, and we're ready to go. Now let's go back to the diagram and begin our program. The first thing that we would like to do is generate our sine waves. So we'll go into our signal processing palette. We'll create our sine wave by selecting the sine wave function, and then we'll drop it down. Now we're going to need two independent sine waves, so let's create a copy of this, and we'll just put it below the other one. Now we'll bring up the help window so that you can see what we're going to wire up and what those values are. The first thing that we would like to do is tell it information about our sampling rate. So we're going to create a constant, and we're going to tell it that our sampling rate is going to be 20,000, and we're going to have 10,000 points in the waveform. We're going to share this information between each of these VIs. So we'll just go ahead and move this over a little bit, and then we'll wire that same identical information into our other sine wave. So now we've got that set up. The second thing we'd like to do here is set the frequency of the sine wave, and let's generate a 1 kilohertz tone. So we'll put 1000 here, and that'll be a good tone that you can hear audibly from the amplified speakers. We'll share that among both of our sine waves as well. The next thing that we would like to do is tell it that every time we iterate in our loop, we want to reset that signal. And the reason we do this is because the function will require a reset if we want to change the phase. Otherwise, it would maintain phase consistency through each iteration itself. So we'll just tell it, yes, we want to reset the signal every time. Okay, so we're good there. The next thing that we want to do is create controls for each phase value of the inputs. But since we've already created those from the front, we'll just go and wire those right into the sliders that we've created. So we'll wire from our phase over to slider 1, and now from the front panel we can use that control to set the phase. And then we'll take the second slider and wire it independently into our second sine wave. And if we clean that up, we'll see that everything looks a little bit better. Alright, now what we want to do is merge these signals together. We have two independent sine waves. They can now be controlled with independent phase, but we want to combine those because we're going to send them out our same analog output device. We're going to merge our signals together. So we'll select that from our signal manipulation palette, and then we'll take our output sine waves and we'll send them into our merge function. And now for the actual analog output task itself. We're going to go get our DAQ assistant, and we're going to tell it that we want to generate our analog output signals. So in this case, we'll generate signals, analog output, voltage, and we need to choose the two channels that we want to output. And that's going to set up our analog output task. So at this point, we're set up and ready to go. If we click OK, this is going to generate the code behind the scenes to set up our analog output. And then we're going to take our two sine waves that have been merged together, and we're going to wire that right into our analog output. And now we're set up with our analog output task, and that's good to go. What we'd like to do is put this inside a loop now so that it happens over and over again. And every time it iterates, we'll have the chance to go and change our phase on one of the analog outputs. Since we want this to run until we tell it to stop, we'll create a control, and that will shut that loop down when we're finished. So that's for our analog output. What we'd like to do now is set up our analog input. So we'll go get another DAQ assistant, and we'll put it down on our diagram. And this will bring up some selections that we can set up here. So we'll set a few values. Acquire signals, analog input, we'll read voltage in. And then we want to read from one channel only, because that's the AO channel or AI channel that comes over here into this channel of the 9233. Okay, so next we want to set some values here. We're going to generate or acquire, in this case, continuous samples. So let's choose continuous samples, and we'll tell it to sample 4,000 samples at a rate of 40,000 samples per second. That's all we need to set there, and we're ready to acquire our signal. So the next thing that we would like to do is some signal analysis. Remember, we said we wanted to read the RMS value. And yes, let's put this inside a loop. It's asking this question now. So we've got a loop to continuously acquire our values. Inside here, we'd like to do some analysis. As we decided, we'd like to read the RMS value and see the cancellation of those waveforms. So we're going to click right. We're going to go into our Express palette. We're going to go to Signal Analysis, and there's an amplitude and level measurements VI that we'll put inside our acquisition loop. So inside here, we just need to tell it that we want to read that RMS value, and that's all we need to tell it. So we're set up and ready to go. Next thing we want to do is take the acquired data, wire it into the signal input, and then coming out of there is the RMS value. We're going to wire this to the meter that we put on our front panel so that we can see the change graphically. If we want, we can clean this diagram up with a Control U, and that's our program, two concurrent loops ready to run, and we're good to go. Okay, at this point we're going to push the run button and we'll generate our signals. Now at this point you can see we have our maximum amplitude. The RMS dips in the break in each signal, but we're going to go and increase the first slider. This is a max amplitude because these sine waves are in phase. Let's increase the phase on our first analog output, and you'll see the amplitude drop. Now since we've gone right up to 180 degrees out of phase, we get a minimum amplitude as those two waveforms are combining to reduce each other's amplitude by the maximum amount because they are 180 degrees out of phase. Now if we take our second slider and we update it, we'll see that our amplitude increases because from this point on we can only come into phase increasingly with one another. And you see when they're both at 180 degrees, we get a maximum amplitude. We've inverted the phases, but they're both inverted so they sum to the greatest values. So at this point we'll stop the program, and you've been able to see that we could do simultaneous analog input and analog output with control independently of the phases of these. And this is how you could do noise cancellation with the National Instruments CompactDAQ and LabVIEW.